Let's delve just a little bit deeper into differentiability and talk about how that ties into continuity. So again, we've looked at variations of this exact same function over and over. This is really the same thing. Again, using the derivative of f at c, we'd use x and we'd use c, which is really the same as saying, you know, x plus h or whatever value we decided to use. It doesn't really matter, it's the exact same function. What we're saying is, first of all, if a function is continuous, and again, continuous means there are no holes in the graph, so there's not like a big hole in the middle. There's no breaks in the graph where I've got a graph and then a space in between and then a graph. There's no jumps in the graph where I've got part of a graph and then it jumps. So those would all be not continuous. So this is any continuous function. It's possible that it's differentiable. And it's differentiable on a closed interval, AB, so AB, also known as CX, we get the idea. It's differentiable over that whole interval when the derivative from the right of A and the left of B both exist. So let's look at that looking at our picture. As I look at my first point, if I look at the left of that, I can see it is continuous and there is going to be a derivative. And from the right of that, it is continuous and there is going to be a derivative because I can find the slope of the line tangent at that point. And again, we'll talk more about how to be able to just visually look at a graph and determine this. Let's take a look at something where it is continuous but not differentiable. So here's a continuous function. As we can see, I have a y value for every x value in the domain. But if I look at the function, the derivative, and remember the derivative is really just the slope of the line. So essentially I'm saying, let's look at the point 2. If I looked at the slope of the line coming from the left, so notice that notation, 2 with a little negative on the top means 2 coming from the left-hand side. If I were to look at the slope of this function coming from the left-hand side, any secant line I could come up with would have a slope of -1. The slope from the right-hand side, so 2 with a little plus means from the right-hand side, obviously would have a slope of +1. And again, I've kind of shown you some of that work up here. That's not as important as just being able to visually look at the graph and say, hey, these two things don't match up. So even though this is a continuous function, it's not differentiable at this point, and therefore there's not a tangent line at the point 2, 0, because the left and right hand side limits do not agree with one another. Here's another example, or I guess counterexample, another situation you might come into contact with. Here we have the function f of x equals x to the 1/3, and obviously it's continuous. Looking at the graph, I can see that. However, as I look at the limit as x approaches 0, this point right here, I could say from the left-hand side and the right-hand side, they're sort of the same, but that slope of that line would be infinity. So let's take a look at the math behind that, because a lot of people are like, hold on, hold up, where did you come up with infinity? So let's look at this function, f of x minus f of 0, again 0 because I'm looking at the point 0, over x minus 0. So my function is x to the 1/3, so x to the 1/3 minus 0 to the 1/3, which is 0, over x minus 0, which is x. Then what I have is essentially x to the 1/3 over x, and so I can reduce that by taking 1/3 minus 1, which is -2/3. So notice I have 1 over x to the 2/3. I could just write that as the limit as x approaches 0 of x to the -2/3, but here's why I wrote it this way. It's going to help us visualize what's happening here. If I look at plugging 0 in here, from the left or from the right, so let's say I have x that gets closer and closer to 0. So you can start with 1 or start with 1/2, or sorry, -1 or -1/2 or -1/4 or -1/8 or -1/10. And as I continue to plug those in, what's going to happen to that number? Well, I'm going to get a small, small, small number down here. So it's 1 divided by an increasingly small number. And as I divide by a smaller and smaller number, what's happening up here to the whole function? It's getting bigger and bigger and bigger and bigger. And that's going to be the same from either direction. So because the tangent line is vertical, f is not differentiable. So we've talked about it's not differentiable when you have a corner. That was our absolute value function, even though it's continuous, and it's not differentiable when you have a vertical tangent line. So again, a function is not differentiable at a point at which the graph has a sharp turn or a vertical tangent. So we looked at both of those examples together. And differentiability implies continuity says if our function is differentiable, it must have been continuous. So we talked about the fact that just because it's continuous doesn't mean it's differentiable. Here we're saying because it's differentiable, it is continuous. So again, summarized here in our 2 points, if a function is differentiable at the point x equals c, then it's continuous at x equals c. So differentiability implies continuity. If it's differentiable, we're saying it is continuous. It is, however, possible for a function to be continuous at the point and not be differentiable because it might be a sharp turn or it might be a vertical tangent line.